Welcome to the Deep Dive. Today we're tackling a really fascinating question, something that gets right to the core of how these advanced AIs work.
Yeah, we're looking at spontaneous topic changes. How do these language models jump from one idea to another?
Exactly. We've got some notes here dated May 19th, 2025, and more importantly, this really quite groundbreaking research paper.
That's Dynamics of Spontaneous Topic Changes in Next Token Prediction with Self-Attention.
Quite a title. It is. And our mission today is to really unpack the innovative parts of this research. How does it help us understand these topic shifts in AI, especially compared to, well, how our minds jump around?
And the spoiler, maybe, is that they don't really seem to jump around quite like we do.
Right, that's the big surprise. The paper suggests that the longer these models think or process information on one topic, the less likely they are to spontaneously shift away, which feels, well, very different from human experience.
Totally different. So yeah, we're diving deep into the actual mechanisms, the architecture, to see if these AI transitions look anything like our own, sort of intuitive leaps. And this paper gives us a really novel way to look at that.
Okay, so let's set the scene a bit. Human thought. It wanders, right? Neuroscience tells us this kind of spontaneous thinking is just, well, fundamental.
It's how we make connections, how creativity often works.
Think about Gabriel Garcia Marquez, the start of 100 Years of Solitude. It goes. Many years later, as he faced the firing squad, Colonel Aureliano Buendia was to remember that distant afternoon when his father took him to discover ice.
Wow. Yeah.
Just like that, fire squad to discovering ice. A huge leap feels totally spontaneous. That sudden, unexpected jump feels so human.
It really does. It's associative, unpredictable.
So the paper asks, can our AI buddies do that? And what they found is, well, maybe not in the same way.
Right, because large language models, they're usually built to follow context. You give them input, they predict the next likely word based on patterns.
Like figure one in the paper shows, right? They fed that same Marquez sentence to GPT-2.
And it just continues the story about the firing squad. Makes perfect sense contextually, but there's no surprising leap. It stays on track.
Exactly. Coherent, but not spontaneous in that human way. Which brings us squarely to the paper, Dynamics of Spontaneous Topic Changes, by Mumin and Jairo Diaz-Rodriguez at York University. What's the big innovation here? Why is this paper different?
Well, the main thing, I think, is that they actually try to formally define and measure spontaneous topic changes using the self-attention mechanism that's the core of how these models work. And then they directly compare these dynamics to human thought.
Okay, so they're not just looking at the output, they're trying to model the process.
Precisely. And that comparison to human cognition, that's the really novel angle. A lot of prior work maybe observed topic shifts, but didn't try to align the mechanism so closely with models of human thought.
Okay, so how do you even start to formalize something like a topic change inside an AI? Sounds tricky. They needed a specific framework.
They absolutely did. And to make the math work, to do a rigorous analysis, they started with a simplified model, just a single layer of self-attention.
Right, simplify to understand the core principles. Building on earlier work.
Exactly. They mentioned folks like Li et al., Tarzana et al., whose work laid some groundwork for analyzing these attention mechanisms. But here's the really innovative step, I think.
Go on.
They introduced something called token priority graphs, or TPGs.
Okay, token priority graphs. What are those exactly?
Imagine a topic isn't just a label, but like a network, a mind map, maybe. Certain words or concepts, tokens are central, others are more peripheral but still connected. These TPGs are their way of mapping that structure within the AI's attention system.
So a topic becomes this structured set of graphs, not just a fuzzy idea.
Yes, and that's key. It's a structured graph-based formulation. They drew inspiration from things like attribution graphs, which people use to figure out why an LLM made a certain prediction, and then even neuroscience models about how we organize concepts.
That connection to neuroscience is interesting. It really highlights their goal of comparing AI and human processing.
Definitely, and once they have this TPG framework, they can define topic continuity. That's basically when the AI's next prediction stays within the expected network, within the TPGs of the current topic.
Got it. So a structured way to measure if the AI is staying on topic based on its own internal representation. So with this innovative framework setup, what did they find? What did the theory predict?
Okay, so some really key findings came out of a theoretical model, and some are, well, not what you might expect. First, there's Theorem 3 about the preservation of input topic priorities.
Preservation, meaning it sticks to the original topic.
Essentially, yes. Even if the model knows about multiple topics, if you give it an input that's clearly about topic A, its internal attention mechanism keeps prioritizing the key elements of topic A.
Like an oracle. If it knows A and B, but you asked about A, it focuses on A.
That's a good analogy they use. Even with knowledge of topic B, its focus stays on topic A based on that input. Figure 3 in the paper shows us the probability distribution stays focused. Appendix D.5 has the number crunching behind it.
Okay, so a kind of topic inertia or stickiness. Interesting. What else?
Well, Theorem 4 looks at what triggers a change, and this is where it gets kind of weird.
Uh-oh. How so?
It turns out a topic change, in their model at least, is more likely if the lower priority tokens from the original topic show up more often than the higher priority ones.
Wait, hang on. The less important words appearing frequently cause a shift, not the core concepts.
Exactly. They define this thing called the highest priority SCC. Think of it as the absolute core kernel of the topic. If the input keeps repeating words that are related but not part of that core kernel more often than the core words themselves, that can push the model off topic.
Huh. That is counterintuitive. It's like the background noise drowning out the main signal.
Sort of, yeah. It's like the repetition of the less defining elements erodes the focus on the main topic. Again, Figure 3 has an example, and Appendix D.5 backs it up numerically.
Fascinating. Not a strong pull to a new topic, but a weakening of the old one by peripheral stuff. Okay, now, you mentioned the really crucial findings involve context, length, and ambiguity. That sounds like where the human comparison really diverges.
Absolutely. This is Theorem 5. And honestly, this is maybe the most striking innovation and difference they highlight. They found that longer input sequences, more context, actually decrease the likelihood of a spontaneous topic change.
Get out of here. Seriously. More context makes it less likely to wander.
That's what their theoretical model predicts. For humans, you'd think a longer train of thought offers more chances for tangents, right? But for the LLM in their model, more context seems to just anchor it more firmly to the initial topic.
That's the opposite of my brain trying to write an email. Okay, what about ambiguity? When topics overlap, humans often jump between related ideas then.
Right, you'd expect more overlap, more ambiguity to maybe grease the wheels for a topic shift, but nope. Their theory suggests the opposite for LLMs.
So more overlap doesn't mean more shifting.
It does not increase spontaneous shifts and might even decrease them. More ambiguity doesn't make the model jumpier. Figure 4 shows simulations backing this up, and tables 1 and 2 have the proportions. They even mention the law of large numbers.
Meaning, with more data points in a longer sequence, the statistical patterns just get stronger and resist deviation.
Pretty much. It reinforces the dominant pattern. So yeah, longer context, more ambiguity factors that might make a shift topics seem to make these models less likely to shift spontaneously. A really fundamental difference.
Wow. Okay, that's a stark contrast. But this is all based on that simplified single-layer model, right? How do we know this isn't just an artifact of the simplification? Did they test it on the big guys, the real LLMs?
Excellent question. And yes, they did. That's the crucial next step, seeing if these theoretical insights hold up in the wild with complex state-of-the-art models.
Which ones did they use?
They used a bunch of recent heavy hitters, GPT-4o, Llama 3.3, Claude 3.7, DeepSeek-V3. They specifically chose models and evaluation data arXiv papers from March 2025 that the models likely hadn't been trained on directly.
Smart. So the papers act as distinct topics. And how did they control what the models knew? You can't just retrain them.
Right. They used retrieval augmented generation, or RAG. This let them feed the model specific information either from just one paper for a single topic focus or from 2 different papers to create a mixed topic context.
RAG. So they could precisely control the knowledge base for each test. Okay, so what were the experiments?
2 main ones mirroring the theoretical findings. First, input length. They fed the models increasingly longer bits from a paper's abstract.
And measured?
They measured topic continuity using cosine similarity. Basically, how similar was the text generated by the model when it only knew about paper A versus when it knew about paper A and paper B? Higher similarity means it's stuck closer to topic A.
And what happened with longer inputs?
Just like the theory predicted, Figure 5a shows it clearly. Across all these big models, the cosine similarity generally increased with longer prompts. More context led to more topic stability.
Wow. So the big complex models showed the same pattern as the simple theoretical one. Longer input, less topic drift.
Exactly. It supports Theorem 5 empirically.
Okay. And the second experiment, ambiguity.
Yep. They kept the prompt length the same, but varied the ambiguity between 2 papers. They measured ambiguity by looking at the similarity of keywords between the papers. Higher keyword similarity meant less ambiguity, more distinct topics.
And they checked the cosine similarity again.
They did, and again, it lined up with the theory. Figure 5b shows that the cosine similarity did not decrease when ambiguity was lower, meaning when topics were more distinct. If anything, it sometimes increased slightly. So more overlap between topics didn't make the models jump between them more readily.
So increased ambiguity didn't cause more topic shifts, just like the theory said. That's pretty solid validation then.
It really is. The fact that these complex frontier models empirically showed the same dynamics predicted by their simplified theoretical model is quite compelling. It suggests this isn't just a quirk of the simple model, but maybe a more fundamental property of how self-attention-based LLMs handle topic dynamics.
Okay, so let's try to wrap this up. The big takeaway from this deep dive seems to be that LLMs, even the really advanced ones, show patterns of topic change that are, well, fundamentally different from us humans.
That's the core message, particularly around how context, length, and topic overlap affect things. They just don't seem to work the same way in these models as they do in our heads.
And these findings are surprising, right? Counterintuitive even when you think about your own mind wandering.
Definitely counterintuitive from a human perspective, and it really makes you think about what's going on under the hood of these AI systems.
It really does. So for you listening, what are the implications here? How might these differences affect how we talk to AI, how we design AI in the future?
Right. If we want AI that feels more natural, more human-like in conversation, maybe we need different architectures, ones that can replicate that more fluid, associative shifting we experience.
That's a huge question. And it leads to maybe a final provocative thought to leave you with.
Could this basic difference in how topics shift, how context influences focus? Could this be a clue, maybe a key difference that explains why current LLMs, despite being amazing at language, don't seem to possess understanding or consciousness in the way humans do?
Ooh, that's a deep one. Is this difference in topic dynamics a fundamental barrier? Something to ponder. Thanks for joining us for this deep dive.
Yeah, fascinating stuff. Thanks for exploring it with us.